Now, when you have the diode, so let's just take, for example, we designed a circuit, alright? Let's just say we have an alternating current. This is the symbol for alternating current. And then we have our diode in the circuit. Let's say we have our diode in the circuit and it looks like this, for argument's sake. Let's put a resistor here, etc. What you now find is that the result that is going to be across this is going to look like this. It's going to look like this. So it's not going to allow the negative portion to be outputted. So it cuts off the negative portion and it only allows the top half to flow in through the resistor. So that's kind of like what we're saying. It only allows current to flow in one direction. So whereas you have the alternating current, right, which goes up and down and everything, once you put the diode in the circuit, yeah, it now prevents the negative portion from flowing to the resistor. Is that clear? Are you sure? The direct current, exactly. Yeah. This is not perfect direct current as you can imagine. Direct current will generally look like this. It's just a straight line, but you can still consider this as direct current because direct current means in one direction. It doesn't necessarily mean whether it is a consistent flow of current, but it just means that it's in one direction. But this is ideally what the direct current would look like. That's what you'll get from a battery, right? But when you have the diode in the circuit, it performs what we call rectification, and this is what we call half-wave rectification if we use in one diode. But that is a whole different scope of electronics in itself. But what I want you to see is in terms of what the graph looks like. The graph depicts how the device works. We said that the diode acts as a switch, which means that there is a point to which it will turn on and there will be a point to which it will turn off. So let's look at it. So if you look carefully, you would see that it says that for a small potential difference, the resistance is very high and therefore no current flows. So if when I connect my circuit, if my power supply has not provided enough potential difference, then it simply means that no current will be able to flow because there will be simply a very high resistance in the semiconductor diode. However, if I increase the potential difference up to a point, yes, then you find now that there is going to be a level to which current starts to flow, and that is now when we say that the diode is turned on. Alright, so it's now acting as a switch where it was off at first and now it is completely turned on. And so with that being said, we can clearly say that the diode is in what we call forward bias. Alright, so forward biasing is when the diode is actually turned on and when it's actually working. Yeah? You need to also understand that it can also operate in the negative region as well. And so you'll find that when you go to the sixth form level, you'll learn a little bit more about it, but it says here that the resistance is very high when the potential difference is applied in the opposite direction. And that is just telling us that the diode is in reverse bias. Now, in reverse bias, it does not turn on unless you increase the potential difference up to a very, very high level. So it might be about 50 volts. If you increase the potential difference up to 50 volts, you'd find that you will be damaging the diode, and that's when it's actually going to work. But generally speaking, it does not work in the negative region. You understand?